reduction to exact form by integrating factors. Yeah. How to find that special factor? Yeah. All right. We need to develop some systematic method to do it. Yeah. Consider this differential form, yeah. PQ function. Okay. All right. Yeah. So this condition. Yeah. We target. So we assume this condition. All right. Yeah. So, oh yeah, we're halfway. Oh, actually yeah. So we finish this one, then we need to move to this side. Yeah. All right. Yeah. All right. That side. Now, we imagine there is some special f function we can multiply on the left-hand side. But this f function is unknown. We need to determine this capital F function. The criteria used to find the f function equal sign. Okay? Yeah. Equal sign. Yeah? Require, so this is the condition, requirement. Yeah. After we multiply the f function, we have the exactness criteria. Yeah, yeah. The logic is very simple. Yeah. But the question is how to find appropriate capital F such that this equality holds. Right? That may not be easy. Yeah. So let's take partial derivatives, both sides. By a simplified notation, yeah, because in math, notation is very important. If you use good notations, you can find some interesting properties easier. If you use bad notations, you get overwhelmed, very messy. So you couldn't see any interesting properties. Here we have that situation. Yeah. Because we can apply the product rule. Yeah. Partial derivative product rule, yeah. So we know how to. But if you use this partial way, yeah. If you use this partial way, both sides, then too complicated. Too complicated. Yeah. So we want to use a simplified way, still partial derivatives, but in a simple way. Yeah. Subscripts. We can use subscripts for partial derivatives, right? Yeah. Here we use subscripts. Yeah. The same thing, product rule. Yeah. Partial f over partial. We write this f sub y. Yeah. Simple. Yeah. We do not change anything. Yeah. But the notation difference, it's important here. Okay? Yeah. All right. Now, you can see there are 4 terms. Each term is a product form. Product of 2 functions. Product of 2 functions. Yeah. Yeah. And, yeah. P function is known. Q function is known. P sub y function is known. Partial derivative. Yeah. Known. Q sub x is known. Yeah. But f function is unknown. F sub x unknown. F sub y unknown. Yeah. It's pretty hard, right? Yeah. When you determine f function, you need to consider f sub x and f sub y. Yeah. Too much uncertainty here, right? Too much uncertainty. Hard to control. Yeah. Question, how to simplify it? We want to simplify it. Yeah. Because first, we remember for this ODE, we may not be able to find F that satisfy this condition. We may not be able to do it. Only when we are very lucky, we can make it work. But most of the time, we're not that lucky. Most of the time, we're not that lucky. So we cannot make it work. Yeah. So here, based on this understanding, you can imagine we only need to target the special cases. We do not target the general cases. General cases is too hard, right? But special cases, think about, under certain special conditions, you'll make it work. Only under certain special conditions, you'll make it work. Think about that. Yeah. That means you can make some special assumptions here. Make some special assumptions here, yeah, to make it work. Okay. All right, too complicated, yeah. So we just consider relatively simple cases. Yeah. So here we consider under what special conditions we can greatly simplify this complicated form. Too complicated. Okay. All right. So further simplify it, can we consider a special case that f function is only a function of x, but not a function of y? That's a special case, right? Yeah. Yeah. Too special. Yeah. Although too special, but let's try this special form, special case. Yeah. Too special. Yeah. We agree it's too special. Yeah. But let's try under this assumption, do we have a chance to get it to work? Okay? All right. Because under this assumption, partial f over partial y, it's 0. So this term is gone, right? Yeah. Yeah. Because the four-term equation too complicated. When we make this assumption, partial f over partial y, 0. It's gone. Okay? Yeah? Yeah. So we get this simpler form. F times p sub y equals f prime times q plus f times q sub x. Okay? Yeah, F we can combine, right? F we can combine, right? Yeah, yeah. So, all right. So we do some manipulation. We get f prime over f equals a known function. Yeah, right hand side is a known function. P sub y minus q sub x over q. This is a known function. Okay, that means you only need to determine a special function capital F such that f prime over f equals a known function. Yeah. There is a possibility, right? There is a possibility. Yeah. But still, because f function, it's a one variable function with respect to x. So f prime over f is also a function of x. No y, right? Yeah. Look at the left-hand side. F prime over f, it must be a function of x and no y based on our assumption. Then right-hand side, yeah, right-hand side must be a function of x and no y. Otherwise, you cannot make it equal, right? Right-hand side contains the variable y, but left-hand side does not have the variable y. How can you make them equal? Yeah. So you need to calculate this fraction to see if it is a function of only x. If it is, then you can solve it for f, capital F. If not, most of the time it's not, right? Only in a very special, small percentage case, you can, after you calculate this fraction, you get a function of x. Then you can solve for capital F. Yeah. All right. Yeah. But that is the, yeah. So you let R function, yeah, you define your capital R function as this function, that function. Okay? All right. So you want to see if is this R function only contains variable x, no y. Yeah. One variable function about x, no y. Yeah. Then, if it's true, you can solve this equation, f prime over f equals r. Yeah. That's an easy ODE. That is easy ODE. Okay? Yeah. Yeah. All right. Yeah. Yeah. So that's the, basic idea. Okay? All right. Then, because if you solve this equation, you can write f function as a exponential e function. E, okay? exp. That's the e function. The exponent is the integral of R function. Integral. E to this integral function. Yeah. So you find f. After you find the capital F function, you multiply, you make it exact, then you solve this exact ODE. Yeah? That's the basic idea. Yeah. You make assumption, you assume capital F function is a very special, simple function. One variable function. Why? Yeah, so f is a one variable function. Why you only consider f is a function of x, not y? Only consider it's a function of x, not y. Yeah. Can you also consider your f function is a one variable function of y? No. Similar idea, right? Yeah. Yeah. So there is another possibility. Yeah. So this is first special case. Then you have second special case. Yeah. So you can also solve a second. So these two special cases, we can find a solution. We can solve this kind of non-exact ODEs. Yeah. All right. Yeah. So here, yeah. So this is yeah. So we get to this point. So here I want to talk about f is a function of y. Yeah. Yeah. In that situation, f sub x, this term is gone. Okay? That term is gone. Yeah. So we have this simplified form, but the f here, we can combine these two terms. Yeah. Okay? Yeah. So we get this. So this time, left-hand side is a function of y, but the right-hand side, it should also be a function of y so that we can find capital F function. Yeah. So this time we use the R star symbol to represent this special fractional function. R star, okay? Yeah. Different from R. Yeah. R star, if it is a function of y, then we can solve this ODE for capital F. Yeah. Then the solution you can see, yeah, so it's f of y equals e to this integral of r star of y. Yeah. Yeah. So that's the second chance. Yeah. So for these two special cases, you need to check capital R star, yeah, if they are one of the two. Yeah, one of the two. Yeah. If one of the two satisfy the condition, one variable function, the condition, then you can make it work. You do not need both one variable of two, right? One variable function. Yeah. Yeah. If one of the two satisfies the condition, then you can find a solution. Yeah. All right. But if both functions are not one variable function, if both functions are two variable functions, then this method fails. This method fails. Okay? Yeah. Yeah. All right. Summary. Yeah. So you calculate two functions, R function, R star function. Okay? You calculate two functions. If the R function is a very, yeah, so is a very, is a one variable, yeah, so here I put it in the parentheses, function. Okay? Yeah. If R is a one variable function, yeah, but that should be, the variable should be X, yeah, not a Y. Okay? If it's a one variable function, but it's a variable of Y, then it fails. Yeah. So it's a one variable, that variable must be X, not Y. Yeah. All right? So that's the first case. Second case is a one variable, put it in a Y, yeah, one variable function. Okay? Then yeah, you can solve for capital F function. Okay? All right. If both work, yeah, there is a possibility. Both, yeah. These two conditions, both conditions are satisfied. Okay? Yeah. Then you can take one of the two. Yeah. Both works. Both work. Yeah. Both you can find a capital F. So under this condition, you take the easier one. Yeah. Yeah. Because one should be usually, most of the time, one should be easier than the other. Because one is a constant, then it's easier. Yeah. If one you see a complex function, but the other one is a much simpler function. So you want to choose that simpler function. Yeah. If both work, then easier one. Yeah. 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 So you solve the, after you determine capital F, then you solve the exact ODE. Yeah. Yeah. So that's the summary, yeah, for this method. Yeah. All right. Then we do one example. So we complete part D. Yeah. One example to show you this method. All right. Reduction to exact form. Yeah. Solve this ODE. Yeah. Yeah. Yeah, because at the end, if there is a constant, we need to use this initial condition to determine the constant. Yeah. All right. P function, Q function. All right. Yeah. So the PQ. So let's calculate. Yeah. Remember, based on the summary, we need to calculate R function and R star function. Yeah. R function, let's calculate R, partial derivative. Yeah. After simplification, you get this function. Two variable, right? x and y. So this way doesn't work. Yeah. All right. Second way, r star, constant. Yeah. It's a very simple f function we can find. R star. Yeah, we need to use R star function here. Okay? Yeah. So to calculate integrating factor, yeah, using R star, yeah, because e to the negative y. Yeah. All right. And here, yeah, make some simple comment here. All right. Integral exponent is integral, indefinite integral. That means you may need some constant, right? Yeah. Indefinite integral, usually you need to include some constant here. All right. So the constant, there is a constant in this exponent part, that means there is some constant in front of this function, right? Yeah. But here, we skip that constant. So here you can see, we do not include that constant part. No. Why? Because for the integrating factor, our goal, we want to choose an integrating factor, right? And when we choose an integrating factor, we want to make it as easy as possible, right? Yeah. To make it easy, we make this constant 1. We don't want to make some random number as the constant here, right? So, yeah, because we put a 1 there, that's the easiest form, yeah, for integrating factor. Yeah. So here, don't worry. So the constant case, yeah, yeah, because we only need to choose one function, right? Yeah. Think about what's the reason we consider adding constant when we take integral, when we calculate integral. We want to find a general solution. The reason we include a constant, we want to find a general solution. Here, we don't want to find general. We only want to find a special solution. We only want to find one special solution, not general. So we don't need to include a constant. Yeah. So the constant is for the general solution. Then you want to cover, all possible cases. That's why you include that constant. Here, we don't want to cover all possible cases. We only take one special case. It's enough. Yeah. So that's why no constant. Yeah. All right. Then, now, multiply this integrating factor. Yeah. Both sides, simplification. This time it should be exact. Okay? Exact. Yeah. So you check the condition. Yeah. Both numbers 1. Okay? Yeah. So there you calculate. Yeah. Yeah. First form. Yeah. So some little k function. Second form. Well, this one. Little k. A little l function. All right. Then. Yeah. So let's use our simplified method. Okay. Yeah. So simplify. We want to write the final u function form directly from these two forms. Okay? All right. Common terms, right? Yeah. Common terms. We keep the common terms. Yeah. All right. X term, this e to the x should go to capital little l, right? Yeah. Corresponds to this little l. This e, this corresponds to that little k. Okay? Yeah, y function. Yeah. So this, that, there, right? Yeah. So then when we write this function, yeah, so little k function, little l function, little k function, and the common terms. Yeah. So, yeah. And we do not miss anyone. All right. So when you write this form, we do not miss anything, right? Yeah. We cover everything. Yeah. We cover everything. Yeah. All right. The right-hand side is constancy. That's the final solution. Yeah. So it's pretty easy, right? Yeah, it's pretty easy. So we do not need to take partial derivatives to calculate these two functions. Although you can do it, yeah. But based on the observation, yeah, you can write it immediately. Yeah. So another example to show you how to use the simplified method. All right, yeah, so we complete this whole example. Although you need to determine the c, yeah, it's a constant c, use y of 0 to determine it. So you plug in x equals 0, 1, okay, yeah, this point, 1 plus, because this term is 0. This term, yeah, because y is negative 1, yeah, y is negative 1. Okay, yeah. So c equals this number. Yeah. So your final solution is this. The solution. Yeah. Equation. Yeah. Implicit equation. That's the solution of the ODE. Yeah. So that's the, this whole method. Yeah. All right, yeah. So we finish part E, part D, okay? Yeah. So there is, this part, extended part, because I can put it in a video, okay? Yeah. Put it in a video. All right. Don't go. So we still, because we have at least 15 minutes. So I want to do 15 minutes on part E, okay? Yeah. Yeah. Because we don't want to waste time. Right? Yeah. So now let me jump to part E. The last part of module 1. All right. All right. Yeah. Topic. Slow. What's wrong? Oh, good. Yeah. The title, Bernoulli equation and the population dynamics. Yeah. So E.1, linear first order ODEs. Yeah.
I don't think part E is released yet.
Oh yeah, not released. Yeah. Yeah. So I will post, yeah, because the supposed to be next class, the top, yeah, so I didn't post it. Yeah, but after this class I will post it. Yeah. Yeah, 15 minutes. Yeah, we can do 15 minutes. Yeah. Not released. Right. Yeah. First, let's consider linear first order ODE. Very simple, but we need to know what's the definition of the linear first order ODE. Yeah. All right. Here we consider this special form. Y prime plus P function. Yeah. So P function, yeah, you can put different P function there. P of x times y equals another unknown function, R function. Yeah. But in the specific questions, these two functions will be given. Yeah. But you can see this simple first order ODE, also linear, first order ODE, linear, yeah, you can see you need some techniques to solve. Yeah, you need some techniques to solve. Okay, all right. Yeah, so linear. Yeah. Why we call them linear? Yeah. So here, let me give you the conditions. Yeah. Yeah. All right. The structure of a linear function. Yeah. With respect to a variable x, a linear function has the form ax plus b. That's a linear function. With respect to x. Yeah. Yeah. First, you need to determine what's your targeting variable. So here, x is our targeting variable. So a constant times variable x plus b constant. Linear form. Yeah, very simple. Yeah. But then, based on this understanding, we want to understand this linear ODE. With respect to y, yeah, because you need to determine your targeting variable first. Okay, the targeting variable first. Yeah. All right. With respect to y prime, yeah, because here there are two potential targeting variables. One is y prime, another is y. Okay, all right. With respect to y prime, it is linear. Yeah. It takes, yeah, because other than the y prime, all other things you can treat it as constant, right? Yeah. Because if you set y prime as your targeting variable, all other non-y prime terms, you can treat them as constant. Okay? Yeah. So that you have the linear form. All right? Yeah. It's a linear. Then, with respect to y variable, all other non-y terms can be treated as constant. Yeah. Can be treated as constant. Then you have another linear term. So it is linear. If both linear, then your equation is linear. Yeah. No. All right. Yeah. First, we call it first order linear. Yes, here. Right. Yeah, because we talk about linear, right? So we should not miss that linear. Okay? Yeah. Yeah. Or here, or, yeah. Here or here. Yeah. Yeah. Okay? Yeah. Yeah. In engineering, little r function is called input. Yeah. Y function is called output. Yeah. So you have a system. Yeah. So you're working on a system. Yeah. So little r function is treated as the input. Yeah. P function is a part of the system. Okay? Yeah. So there is, part of a system. Yeah. So output function, y function. Yeah. Homogeneous linear ODE. R function is 0. Yeah. Homogeneous. Yeah. R function must be a 0 function. Yeah. Homogeneous. Yeah. R function non-zero, no, yeah, not homogeneous. Okay. All right. Separable structure. Yeah. Yeah. Because for this homogeneous case, it's a separable structure. You can solve it as a separable ODE. Yeah. Yeah. So yeah. You can find a general solution. So this is the general solution. Yeah. Here you can see, yeah. So let me just make some comment. Because when we write this form, there is absolute value. Right? Yep. Absolute value of y. So two cases, positive, negative, two possible cases for y. Yeah. But when we write the final solution, we want to make it as simple as possible, right? Yeah, as simple as possible. Yeah, yeah. So that two possible signs plus minus two possible signs. Yeah, we need to include the positive, negative cases. Yeah. But here, yeah, because so here, yeah, everything together, there is a constant, right? Yeah, we need to multiply a certain constant in front of this e function. Before that e function, we need to put a certain constant. Yeah. But when we put that constant c, it covers positive case and a negative case, right? Yeah. Little c could be positive number, and the little c could be negative number. So it covers both cases. Yeah. So at the end, is little c a positive number or negative number? It is determined by initial value of y. Yeah. When the initial value of y given, you can determine little c. Okay? Yeah. You can determine little c. Yeah. Yeah. So initial value. Yeah. Okay? Yeah. Yeah. Sometimes you may, based on the initial value, your little c may be negative. Sometimes when your initial value is positive number, so you may get the positive c. Yeah. So after we write this form, yeah, so we don't worry about that absolute value. Yeah. Positive, negative cases. Yeah. All right. Yeah. That's the homogeneous case. Yeah. Yeah. Initial condition. All right. Non-homogeneous linear ODE. Yeah. R function, non-zero function. Yeah. All right. So this is finding an integrating factor. Yeah. Finding an integrating factor. Yeah. It works. Yeah. The good thing is, yeah, for this structure, it works. Yeah. All right. Yeah. So rewrite, you consider, yeah, this case, two types of integrating factor. Yeah. So use our old method. Yeah. All right. So here, okay, one is that f. Yeah. So we just, do that. Yeah. All right. Another is this. Yeah. So then use this criterion to determine. Yeah. So you can see the first one works. Yeah. First one works. Yeah. So can you see it? The first one. P. Yeah. See? PQ, right? PQ. Okay. Yeah. Yeah. So yeah. So let me show you how to see it. P Q1, right? Okay. Q1, this is gone, right? So 1, yeah? This is gone, so then Q is 1, right? Yeah. So F prime, right. So what you get is F prime over F equals P sub y. This is a P function. P sub y, it's a little p function, right? Yeah. So it is a function of x. So it works. So if you check, yeah. So for that reason, yeah, you can find integrating factor capital F. Yeah, because the condition is satisfied. Yeah. All right. Then you can find a capital F. Yeah. So here, yeah. Yeah. Actually, we calculate here. Yeah. After simplification, yeah. So you get this function. Yeah, but that function is little p. Yeah. Little p, you can find a solution. Yeah. Capital F is that E function. Yeah. So this function you define it as little h. You calculate this integral of little p and you call it h function. Yeah. That's the, so your integrating factor, you use e to the h. E to the h. Yeah. Okay? All right. Because integrating factor, here you can see absolute value plus minus sign, but we just take one special case, right? Yeah. So we take the plus one. We don't take the minus one. Yeah. Because we don't want to be general, right? We only want to have a special example, special case. So we pick the simplest one. Yeah. So this is the simplest one. All right. Then we multiply that integrating factor both sides. Yeah. Okay. Yeah. So when we solve that u, all right. So m function. Yeah. So this is m function. Yeah. And yeah. Then calculate integral. Yeah. So this integral. Okay. Yeah. M. Yeah. So that's this one. Yeah. First form. Yeah. Second form. Yeah. Little L function. Little L function. Yeah. Then the last one. Yeah. You can see the last one. This x function corresponds to the little l. Okay. K function, because there is no y part, so this corresponds to 0. Okay. Then we write this C. Okay. Yeah. It can be solved. Yeah. So you just, this special first order ODE can be solved. Yeah. You just do some standard calculation. Yeah. Okay. Yeah. Yeah. You calculate it carefully, so then you won't miss it. Yeah. Yeah. All right. Yeah. So that's this slide. Oh, yeah. So we do not need to. Yeah. We just complete this slide. So that's enough. Okay. So next time we complete the remaining part, and I estimate after we complete it, we should have half an hour, so we can start module 2. Yeah. Yeah. All right, that's it. Oh, yeah. Oh, yeah. This is our first class. So the second class, then I will, give you so we will do the homework assignment. Yeah. So this one, so I talk about that next class, homework assignment.